Consider two identical twins, A and B. Twin A remains on Earth living a normal life, while twin B embarks on a voyage aboard a spacecraft, moving through the cosmos at a velocity approaching 80% of the speed of light. Upon returning to Earth after this extraordinary journey, a remarkable discrepancy emerges. Though both began as equals in age, twin B, the traveler, has aged less than twin A, who remained behind. This counterintuitive phenomenon is known as the twin paradox. This effect occurs because time does not flow equally for all observers. Under motion, its rhythm changes, quietly separating one reality from another. A traveler moving through space may experience fewer passing moments than someone who remains on Earth, as though time itself has slowed along the journey. This distortion of time, predicted by modern physics and confirmed by experiments, is called time dilation. The twin paradox is one of the most famous thought experiments in physics, and it comes from the theory of special relativity, which was developed by Albert Einstein in 1905. At first glance, the paradox seems impossible or contradictory, but when carefully examined, it reveals deep insights about how time and space work in our universe. In general science, time is a fundamental dimension that measures the progression of events from the past through the present to the future. It provides a framework for ordering occurrences, quantifying duration, and understanding change in physical systems. Time is treated as a continuous measurable quantity in classical physics, often represented mathematically as a parameter in equations, describing motion and dynamics. In modern physics, particularly in Einstein's theory of relativity, time is intertwined with space into a four-dimensional continuum called space-time, where its measurements can vary depending on the observer's relative motion and the influence of gravity. Ultimately, time allows scientists to describe, predict, and relate phenomena within the universe. To fully understand it, we must explore it step by step. Now, from twin B's point of view, he could consider himself at rest and see twin A moving away from him. If motion is relative, why isn't twin A the one who ages less? This is the heart of the paradox. On the surface, each of the twins could claim the other is moving. So why is only twin B younger when he returns? The solution lies in the concept of time dilation. Special relativity tells us that when someone moves at a significant fraction of the speed of light, time passes slower for them compared to someone at rest. This effect has been confirmed experimentally many times. For example, using extremely precise atomic clocks on airplanes or satellites. Mathematically, the time experienced by a moving observer is given by the formula below, where t is the time measured by a stationary observer, t prime is the time measured by the moving observer, v is the speed of the moving observer, and c is the speed of light. This formula shows that the faster you move, the slower your clock ticks compared to someone who is not moving. A common misunderstanding is to assume the situation is completely symmetrical. Twin B can say I am at rest and twin A is the one moving away. This is true while twin B moves at a constant speed, but the key point is that the symmetry breaks when twin B turns around to return to S. Turning around requires acceleration, which is not experienced by twin A. During this acceleration, twin B feels forces that twin A does not. According to special relativity, each twin sees the other's clock running slower while moving at a constant speed. However, when twin B accelerates, his frame of reference changes. A frame of reference is a perspective or system used to measure and describe the position, motion, or behavior of objects. It consists of a coordinate system and a set of reference points that allow an observer to determine how things move relative to one another. For example, when you sit in a moving train and observe another train passing by, your frame of reference, the train you are on, influences how you perceive the speed and the direction of the other train. In physics, frames of reference are crucial because the laws of motion can appear differently depending on whether the frame is stationary. moving at a constant velocity, or accelerating. Essentially, it is the point of view from which observations are made and measurements are defined. Calculations shows that this acceleration, even if brief, and the geometry of space-time causes twin B's total elapsed time to be less than twin A upon his return. Let us imagine a simple version of this journey. Suppose twin B's spaceship travels at 80% of the speed of light to a planet 4 light years away. From twin A's perspective, this takes 5 years. However, using the time dilation formula, twin B experiences only 3 years of proper time. So, twin B only ages 3 years, while twin A ages 5 years. Twin B comes back at the same speed. Again, twin A experiences 5 years. Twin B experiences 3 years. In total, twin A has aged 10 years, while twin B has aged 6 years. Even though twin B feels like his clock is normal, when compared to twin A's clock, he is younger.